organic, uh, you must be remembering that you've actually started up with different types of organic compounds. And you know, organic compounds are basically the ones which are obtained from living matter. They were differentiated from inorganic matter in two ways. There were certain chemical compounds which are naturally found. The ones which were found in living sources like plants and animals, they were termed as the organic compounds. And the ones which came up from the mineral sources were known as the inorganic compounds. Earlier it was believed that inorganic and organic are absolutely different from each other because of the origin. जो mineral source से आ रहा है वो inorganic और जो living source से आ रहा है वो organic. But then later it was found by some of the scientists, like one of them Wohler. He found that ammonium cyanide, you have ammonium cyanide NH4CNO. Basically this is also prepared from ammonium sulfate. So you have ammonium cyanide, which on heating could be, this is like an inorganic compound, which on heating could give urea. So this is one of the most important reactions that was setting up the base for the interrelation between the two, that you can actually have many relations of inorganic and organic, and you can have reactions which can yield organic compounds from even inorganic compounds. Otherwise urea is an organic compound. Then similarly, then this was like done by Wohler. So the name is important for you, the very first, one of the first discoveries. Then we had Kolbe, who actually similarly synthesized acetic acid, and Berthelot, who did it for methane. Berthelot, who did it for methane. The point here is that what do we understand from all these compounds? One thing, that they are the compounds of carbon only, right? And carbon has got the catenation tendency and the small size. There are only two features which favor carbon to form such a big class, which makes you study an extra kind of branch of chemistry, which is organic chemistry, and that is because of small size. So don't blame carbon for having a small size. And then it has the catenation tendency, and apart from it, the size favors its combination with other elements like oxygen, hydrogen, etc. So that is one of the major factors. Other things that you can talk about organic compounds generally is like, you know that they are, we've already discussed too, they are found from the living matter. Another thing is that they are nothing but the compounds of carbon. Then they can be either gases, liquids, or solids. They are generally covalent in nature. Uh, this you must have seen, that highly non-polar, you find polarity also in compounds, and remember that whenever we talk of polarity, means we are talking about charge separation. Kabhi bhi we have a plus and a minus charge difference in any of the compounds, we say that the compound is polar in nature. Wherever plus and minus charge ka difference will come in a compound, we will say it is polar in nature. And here we are saying by and large most of the organic compounds are covalent in nature, and covalent, you know, are the bonds which are formed by the sharing. This is like very elementary. And they are like, some of them are volatile, inflammable, and another important thing is that generally do not conduct electricity. They do not generally conduct electricity. Okay, now let's start off with some of the basic compounds in general. This was just an introduction that you must have got earlier also. The main thing is that whenever we talk of the carbon compounds, we essentially talk about the shapes also. And whenever we talk about the homologous series is like the series which differs from each other by just a CH2 group, and then they belong to the same family. Say if we can talk about alcohols, then you can have methanol, ethanol, propanol, butanol, pentanol, and so on. When we talk about the shapes, essentially if you remember that when you start up with hydrocarbons, the most basic of all the compounds of organic chemistry, you have alkanes, alkenes, and alkynes. Their shapes are by and large dominated by the kind of hybridization which is operative in their structure. Like, let me just take up the most basic examples, alkenes, and then we have alkynes. You know that carbon has a valency of 4, so it should always be surrounded by 4 bonds all in all. So when we are talking about alkanes, I think I did it with you last year, so you should be remembering, alkanes always have an sp3 hybridized structure. Alkenes will always have an sp2, and alkynes will always have an sp. hybridization. Okay, when you talk about their angles, this is 108 degree, 109 degree, 28 minutes. This is your 100 and sp2 is trigonal planar, so 120 degrees, and this is your linear, so this will be 180 degrees. Now if you talk about the percentage of S character, one thing that is important here is that remember that here you have S character and P. What is this hybridization of? S with P orbital. This is S with 2p orbitals and S with 3p orbitals. So basically you have 1 out of 2 to be of S. So it has 50% S character. This has 33.33% S character, and this will have 25% S character. And remember that greater the S character, closer it will be to the nucleus. And if it will be more towards the nucleus, that means it is more towards a positive charge, so greater will be the electronegativity. So all these factors will be utilized for giving reasons at various steps whenever you come across questions on your own also. So remember that greater the S character. So if I ask, electronegativity will be the highest in case of Sp. So generally alkynes will be, they will be having more electronegative character in comparison to the other two. That ways you can just make out. Do you want me to explain the hybridization again? No. Good. Okay. So remember this, at least the S character that. Okay. Now whenever you have in general, remember that this is also a question which is very commonly asked. If you have a carbon which is surrounded by 4 single bonds, it will always be sp3 hybridized. If you have a carbon with attached with a double bond next to it, then that carbon will definitely be sp2 hybridized. Okay, and 1, 2, 3, and it requires an H. This is 1, 2, 3, it also requires. And say if it is surrounded by a carbon which has a triple bond, then that will be sp hybridized. So you do not have to go on to do anything big for this. You can directly state that by looking at the carbon, because sometimes you're asked for the hybridization of a particular carbon number. You will be given an organic compound and you will be asked the hybridization of any particular carbon number. So in this case, and you can also have something of this type. Alright, CH3, let me just end it up. Right? 1, 1. Alright, done. So I mean these are like signifying the hydrogen atoms to complete the valency. Now you start telling me the hybridization again. I repeat, whenever your carbon is surrounded by 4 single bonds, it will always be sp3. Whenever even a single double bond is there, means one double bond is there, then it will be sp2. If there is a triple bond attached to it, it will always be sp. And you know the shapes for all of them along with the angles, so no need for that to be done. What about, so this carbon is, speak up, sp2, sp, sp, sp2, s. Now here for this carbon, remember it's like an addition. If you have a carbon which is attached, which has double bonds on either side, then that will be sp hybridized. Okay, only for that I just drew this. For the rest you could have understood even verbally. And then again this will be sp2 and this will be sp3. So done. So you do not have to go on to do the hybridization as per you've learnt, either by the shortcut method or by the other. Then you also know that the number of sigma and double bonds which are present, normally your single bonds always represent your sigma bonds. Whenever you have a double bond, then in that case you have 1 sigma and 1 pi. And whenever you have a triple bond, you have 1 sigma and 2 pi. Now say if I'm asking you the total number of sigma and pi bonds in this case, then how will you designate? Just look at that. Calculate the number of sigma and double bonds here. Calculate the number of sigma and double bonds. You can just look at it and tell me. See, calculate the number of CC first, because sometimes your CC bonds are you have CC sigma bonds, you will have CH sigma bonds, and you will have CC pi bonds. That's all, right? For CC sigma bonds, how many? 1, 2, 3, 4, 5, 5. This way you will not get confused. This will be 3, 3CH, and then you have 2, 5, 5 plus 1, 6, 6 plus 2, 8. So 8 CH sigma, and then you just count the extra pi bonds now, 1, 2, and 3. When you segregate, the only point that I want to tell you is that when you actually start counting, you can actually get mistaken up. So it is always better to segregate CC and CH bonds separately. The number of CH sigma bonds will be equal to the number of hydrogens only, and CC manually collect, you can count them manually only. So another question can be the hybridization question that I've already asked. So you can be given any kind of a structure and you can be asked the hybridization. That is very simple. Just look at the carbon atom, what is it surrounded with, and just tell the hybridization. You can easily mark the hybridization. The second thing is for the pi and sigma bonds, which is again very simple. Now there are various ways of representing a particular structure also. Like for example, this is the simplest condensed way that you actually do. This is the condensed form. This is the condensed form, right? There can be another form that is like the zigzag form, right? Each of these, this can also be written like this, CH, Br, then you have a CH2 and you have a CH3 here. Or if I simply draw it like this, then you should be in a position to understand that your each terminal is representing your CH3 and each point is representing your methylene group, and just in case if you have a side functional group attached to it, then you know that your carbon will have only one hydrogen. So accordingly you just have to understand. So get a habit of making it. So if I ask you what is this, then if I am not putting anything on the terminal, I am just putting an OH, then that would not indicate that this is a methyl group. Rather this is just an alcohol with what number? 1, 2, 3, 4. So it will be butanol. Normal butanol. So this is a representation of butanol. This is known as the condensed form. This is known as the zigzag form, both of them, right? Both of them are the zigzag. Another way of doing, like you sometimes write them separately as CH3, CH3, and then you can have CH, and then you have a Br and H and H and H. You can just open up the structure. This kind of a structure is known as the structural formula. Sometimes you're asked the structural formula, so then you open it up and just show it. So very simple designations that you taught right at the beginning itself. Then we come on to the different types of organic compounds that we have. When we talk about different types of organic compounds, one is you have an acyclic. Acyclic means they are the open kind of structures. You can have open, and then you can have cyclic or closed ring compounds, closed or ring compounds. When you talk about cyclic now, open, what are the open acyclic types? Like you have alkanes, alkenes, alkynes, the straight chain compounds, you can have alcohols, whatever is without any kind of a cycle. Then you have cyclic. In cyclic now you have different types. You can either have a homocyclic compound or a heterocyclic compounds. The homocyclic compounds are also known as the carbocyclic. Homo or carbocyclic compounds. And then you can have heterocyclic compounds. Hetero name is given whenever you have an atom which is any other atom apart from carbon. Like if you have an oxygen in your ring, then in that case, and it possesses some kind of a cyclic nature of this form. So then this is your furan. Some common names that you should know. Asked many a times in the entrance examination also. This is your furan. Just in case if there is a nitrogen in here, and you can even check them for the Huckel rules whether they are aromatic in nature or not. What is the Huckel rule? You have 4n plus 2. The total number of electrons should be 4n plus 2. So in this case you have 2, 4 and 6. So that way you can always confirm with it whether it follows that or not. Alright, so this is known as pyrrole. and you have another one. Let me just take one more. This will be your thiophene. PHENE. Okay, so these are your heterocyclic compounds. Then you have in homocyclic, when we talk about, you can either talk about alicyclic or aromatic. You can either talk about alicyclic compounds which do not possess an aromatic character, and then you can have aromatic compounds. Now in alicyclic, what do you have? You've seen cyclopropane. What is this? Cyclobutane. All these are cyclic compounds, but they do not have any kind of aromaticity attached to them. Or take up any other, say cyclohexane also. Cyclohexane actually exists in a chair kind of a form which looks something like this. It is either this chair or it is this kind of a chair. Both of them exist in equilibrium. So all these are alicyclic compounds. What kind? Cyclopropane, cyclobutane, cyclopentane, cyclohexane, and so on. When you talk about aromatic compounds, now again in aromatics you have two types. Either they will be benzenoid in nature or they will be non-benzenoid. Either they will be benzenoid or non-benzenoid. Alright, now if you talk about the benzenoid, then in that case you can talk about any kind of a structure which has a benzene. So in this, of course, benzene will be forming a benzenoid kind of an aromatic compound. Then you can also have naphthalene. All these are benzenoid kind of structures. When you talk about non-benzenoid, then in that case it is something which possesses your aromaticity, aromatic character, but like this structure, you have a double bond O here and you have an OH here. This is that of tropolon. There is no need to learn this structure because as it is, you should be remembering all these names by and large. Tropolon is not to be remembered. You can just see that something which is not similar to benzene, but simultaneously something which is not similar to benzene but simultaneously possesses aromatic character will be your non-benzenoid category. Okay, now repeating once again, this is by and large what your organic chemistry is all about. In your organic chemistry, you can have carbon and its compounds. What are those? Of two types, acyclic or you can have cyclic. Whenever you talk of acyclic or open chain compounds, they are nothing but the entire range of what you are studying now. Haloalkanes, alkanes, alkenes, alkynes, whatever you can think of which is open in nature. Then something that you should be knowing about very clearly, because you do not do it in details otherwise. So what you have is you can have cyclic organic compounds. In cyclic organic compounds you have homo or carbocyclic and you have heterocyclic. In heterocyclic, I want you to remember these names because asked many a times in the examination. These are heterocyclic compounds. You have furan, pyrrole and you have thiophene. Alright, furan, pyrrole and thiophene. Now again, sometimes a question is asked here which is like from your basic knowledge that this is not very basic in nature. Why will this not be basic in nature? The basicity can be due to the lone pair of electrons, and if it is not basic in nature, what can be the reason? It may be only because of the non-availability of the lone pair. अगर वो non-available है तो कहाँ busy है? In resonance. This is what you've done in organic chemistry. So just apply your mind and just think a little bit. So you have furan with oxygen, nitrogen के साथ you have pyrrole, and with you have sulfur, you have thiophene. Alright. Then this was like your heterocyclic. Now coming to the homocyclic compounds, you have two types again, alicyclic and you have aromatic compounds. In alicyclic compounds, what you have is, you have simply cyclic compounds of carbon. So, and its family. So you can have cyclopropane, cyclobutane, cyclopentane and so on. When you talk about non-benzenoid, then when you talk about aromatic, you know what compounds are aromatic in nature which follow the Huckel's rule. So now here in this case you have two types, benzenoid and non-benzenoid. Clearly you're doing benzene very much in detail, so you know the benzene structure. Anything which conforms up with the benzene structure are a part of benzenoid, and whatever is aromatic in nature and not similar to your benzenoid structure goes in non-benzenoid. I've just given you one example. So done. Okay, and then there are like various ways of representing. I just did talk about the condensed and the structural formula and the zigzag form. There's another way of representing your molecule, and that is your wedge and dash projection, or that is known as flying wedge projection also. Wedge projection is something in which you have say if I am representing your simple methane molecule, what is your methane? It is CH4. Then in kind of a wedge projection, what you have is any line which is simply like this is on the plane of the paper or on the plane of the board or on the plane of the table, wherever you're drawing. Okay, not to be done on tables. So here you have this is on the plane of the board, and whatever is like protruding out will be shown with the darkened kind of a triangle. This means that this particular atom is coming out of the plane, all right, and whatever is shown with a dotted line or dashed line is at the back of the plane of the board. So your methane, the tetrahedral structure can be represented in this fashion. So remember, whatever is like darkened and coming out, whatever is darkened and put on the plane is like coming out of the plane towards you, and whatever is dashed will be going at the back. This will be important when we take up the stereoisomerism and different types of isomers to have a better understanding. Okay. Otherwise, you can have other forms also that we'll talk about as we move on to different conformers. Now, classification of the carbon atom, something for which you can have difficulty. So just a quick recap of that. Let me just put up an example. CH3, say CH2, C, CH3, say CH3, and then you have CH, CH3, and your CH3. Now here, this is something which is very, very important, because as you doing your 12th standard, each and every reasoning is based on your alpha, beta, 1 degree, 2 degree, 3 degree. Remember that whenever your carbon is attached to only one more carbon atom, it will be 1 degree or primary carbon atom. Whenever it is attached to 2 carbon atoms, it will be secondary or 2 degree. Whenever it is attached to 3, so tertiary and 3 degree. Whenever it is attached to 4, so quaternary or 4 degrees. So here this is your 1 degree, 2 degrees, 1, 2, 3 and 4. So 4 degree. What about this one? 1, 1. जो चीज़ें सिंपल होती है ना उसमें मिस्टेक्स के चांसेस बढ़ जाते हैं because you're very overconfident about it. What about this one? 1, 2 and 3. So this will be your 3 degree. This is your 1 degree and this is your again 1 degree. Right. Okay. So be very careful in checking out the number of carbons which are attached to a particular carbon atom to designate its degree or what kind of a carbon is attached. Then you can also have another one, say I take up another example of CH2OH. Alright. So now this is our functional group. The very first carbon atom attached to our functional group is your alpha carbon atom. The next one will be beta, the next will be gamma, the fourth will be delta. But remember, it should be like this only. Alright, just in case if I put another one, say another example, CH3, CH2, say C, CH3 and OH. Then in that case, where is your alpha carbon atom? Your alpha is this. So there are, I'll just talk about it. So this is alpha carbon atom. This is your beta, beta and beta. So in this case you have 3 beta carbon atoms and this will be your gamma. So remember, whatever turns without any bias, the second carbon atom will be termed as the beta only. Now we have a similar designation for the type of hydrogen atoms which are attached. Hydrogen atoms are also termed as 1 degree, 2 degree, 3 degree and then you can even have alpha, and then you can have beta. For them it is simple. The hydrogen which is attached to the 1 degree carbon atom is your 1 degree hydrogen atom. The hydrogen which is attached to 2 degree, 3 degree is like respectively named as it is. The hydrogen which is attached to your alpha carbon atom is your alpha hydrogen. The one which is attached to your beta is termed as the beta hydrogen. Clear with that? So if I ask you how many kind of alpha hydrogens are there in the structure? 0. So 0 alpha hydrogens in this particular structure. Alright, how many beta? 6 plus 2, 8 beta hydrogens. Okay, similarly you can just find out for the others also. Remember that the hydrogens, whatever is attached to a particular carbon atom, will be named as that. Now you have done something in this class only. For the carbocations, you must have studied 3 degree carbocation, 2 degree carbocation. You know that if I take up this one, and you do them especially in your very first chapter, that's haloalkanes. In haloalkanes, whenever you talk about the reactions of the chemical reactions of haloalkanes, what happens? There the halogen group leaves, and then you attach. You do some kind of a substitution reaction there, because you're taking up one and you're substituting it with another nucleophile. So in this case, what you have is, what gets formed is your carbocation. So your reactivity depends upon your carbocation, because this is your haloalkane. Whenever you react it with something, what happens first? Your R plus X minus is generated. That depends upon whether the reaction will be SN1, SN2. We'll try and talk about it today quickly. But then what happens generally? You have an R plus and you have an X minus. Now, faster, this reaction will be faster only when this R plus is very, very, very stable. Alright? That thing is also there, that R plus is very, very, very much stable. Now for that stability, if you talk about the reactivity of tertiary haloalkanes, secondary haloalkanes and primary haloalkanes, you should be knowing that tertiary is the most reactive, followed by secondary, followed by primary. Okay, what is the reason for that? In this particular case, when we talk about tertiary, you count the number of alpha hydrogens first. This is your main carbocation. Now I am not putting any group. I am talking about the carbocation, because there is a cation on my carbon. So I am talking about cationic charge on my carbon. So I am talking about carbocation. So here my alpha hydrogen will be the first one on the main cation that I am talking about. So the very first one attached is this one. So I have 9 alpha hydrogens in this case. Alright. Then I have how many? That was wrong. So how many? 6 hydrogens. And just in case if it gets printed wrongly in your examination, you know that you have to act smartly. So it will be like 6 here, and in this case you will have only 3 alpha hydrogens. Now depending upon these alpha hydrogens only, you actually can talk about some other effects which we'll talk about later. That is, you can talk about the stability of these carbocations based on 2 effects. One is your inductive effect, and the other is your hyperconjugation effect. I'll talk about both of these effects very shortly, but remember that greater the number of alpha hydrogens, greater will be the hyperconjugating effect and greater will be the stability. For your subjective paper, it works well. Greater the number of alpha hydrogens, greater will be the hyperconjugating effect, because hyperconjugating structures will depend upon कितने आपके पास alpha hydrogens हैं. और वो भी मैं बता ही देती हूँ. चलो hyperconjugation का यहीं पे देख लो. Lest I move on to the next concept. What happens is, because these are the ones which are immediately attached to my carbocation. Alright, you have C, H, H and H. So what happens in this case? This hydrogen will just leave as H plus outside. Alright, so then in that case what will get attached here? It will rather get attached to this carbon. This H leaves as H minus here and comes to the space. So then in that case what will I get? I will get CH3 CH3, H comes here, and I have CH2. Similarly, each in every hydrogen can contribute to that kind of a structure, because you have, say, if this is A, this is B, this is C. Each of hydrogens can go one by one and get attached to that place. So how many hyperconjugating structures then? 3. बात समझ में आई? And then 3 from here and 3 from here. Not even in the subjective paper you need to draw all those, because there is not so much time. But it is only for you to understand. What we have is, I am talking about the stability of this carbocation. Why is 3 degree the most stable? सबसे पहली बात तो मैंने बोला कि उसके अंदर अल्फा हाइड्रोजन्स काउंट करो. इसमें कितने अल्फा हाइड्रोजन्स हैं? 9. इसमें 6, इसमें 3. So clearly one distinguishing factor is the number of hydrogen atoms. Now I have told you another statement that you've written. Greater the number of alpha hydrogens, greater will be the hyperconjugating structures. वो होता क्या है? This is some kind of a conjugation. Conjugation is like something which goes hand in hand. That I give you something and you take it or you share it or you willingly accept it. It is like that kind. So if your alpha hydrogen is present, it would very willingly try to go to the carbon atom which is having the positive charge. Then in that case, what can happen is that your H can just go out and get attached here, and in that case now the CH2 plus is like 1, 2, 3 and 4. It is some kind of a hyperconjugating structure which is getting formed. As this hydrogen has migrated from this position, so you can have the migration of B as well as C. So 3 hyperconjugating structures from one particular kind of a methyl group. Similarly, you can have another one, and you can have, so 9 hyperconjugating structures. And I told you, greater the hyperconjugation or greater the number of hyperconjugating structures, greater will be the stability. ठीक है? And I'll talk about the inductive effect a little later. So, and in this case then how many hyperconjugating structures will you have? 6. The number of hyperconjugating structures will be equal to the number of your alpha hydrogens. So if I do this, now how many structures? Now how many hyperconjugating structures? 5, because now the alpha hydrogens are like 3 plus 2, so 5. And here in this case it remains as this, and if it was CH3, CH2, so now how many alpha hydrogens now? 2, so you will have only 2. So depending upon that you can just compare your carbocations and their stability. इतना याद रखना, जितने alpha hydrogens होंगे उतने hyperconjugating structures बन सकते हैं, and greater will be the stability of that particular carbocation. So if now any question comes on the stability of carbocations, you should be able to tackle that well. Now, what are your functional groups? You know, functional groups are the ones which are generally responsible for giving chemical properties to any molecules. And you have done a wide range of functional groups like alcohol, phenols, alcohols and phenols are like basically your OH. Then you have done haloalkanes, you've done aldehydes, ketones and all that. So those are your functional groups, because each of them has similar kind of properties, but they differ in their sizes and masses. That's obvious, because it's like kind of a homologous series. And all members of the same family are prepared by generally the same method. So that is why you do their preparations separately. Like ketones have a set pattern of getting prepared. Your aldehydes have a different set of preparations. Aldehydes, ketones match up in some places. And then you have alcohols ka ek set preparation. So all those similar family members will get prepared in a similar fashion. That also you know. Now, there is something which is like nomenclature which you do according to your IUPAC. Very rarely I have seen this question of asking the full form of IUPAC also. So you should know that. You do your nomenclature according to IUPAC names. What is that? Your IUPAC or IUPAC, whatever you call that. That is International Union of Pure and Applied Chemistry. Okay, and then in that you know that you give the preference to the longest chain, whichever is there. One single turn is allowed in your carbon. Now you tell me the length of the longest chain in this structure that I am drawing. So we'll take up questions, and as it is you've done nomenclature, should be simple for you. So you have do you want me to put the hydrogens as well? Do you want me? So I mean CH3, CH2, CH2, you have CH, COOH here, CH2, 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 CH3. Now you have to tell me the number of carbon atoms in the longest chain here, which will be counted for the main parent chain. 1, 2, 3, 4, 5, 6, 7, 8 is what you're saying. So because you have your one of the main functional groups here, that will be counted in your main chain, and in fact the numbering will begin from the carbon of your carboxylic acid only, and then you can move here or there wherever you want. I told you one turn is like allowed always at each point, so then in that case you will have the longest chain as this one, alright, and that will be equal to your 6 carbon atoms. So your name will be some kind of hexanoic acid or something. Depending upon what your side chain is, you can just give it the numbering. Another some important things. So remember that if had it been CHO also here, then also it would have started from here itself. Your functional group has to be given preference because your parent name will come from the functional group itself. And then you have the lowest number should be given to the, we should try whenever there is a side group or a side chain, we should always try that the lowest number should be given to that particular side group. Like for example, if I have CH3, CH3, CH2, CH2, alright, CH3, CH3 here, then where will you start the numbering from? From where? From the left side, 1, 2, 3, 4, 5. So that you know the side or the substituents get the lowest number. So that is also to be taken care of. Now just in case if you had an OH here, then in that case where will you start the numbering from? Now you will start the numbering from the right, because you have to take care of the priority order of your functional groups. Because alcohol in your order of priority is located above your methyl or alkyl groups, so that is why you will be giving now the lower number to the one which has a higher preference. Okay, another doubt that I have is that, say supposedly if I have CH3 here, then I have CH2, CH, CH2, CH3, now CH2 and CH3. Now where will you start the numbering from? Where will you start the numbering? This is like very elementary, very basic. You can be given names. This is one of the simplest questions that is asked even in your JAM exam, which should not be a problem ever, because isme to gadbad karna is like, I think, one of the biggest foolishness if you do that. So in this case, whenever you do the numbering, remember that the lowest number should be given to that alkyl group which has the first alphabetically, which gets the priority alphabetically first. So in this case what you have is you have a methyl group and you have an ethyl group. So remember that had it been a CH3 also here, let me just shorten it, then in that case your numbering should be 1 and then 2 here, 3, 4 and 5, unless and until this would have made the biggest chain, which is not the case. So our biggest chain would be this only with 5 carbon atoms, but remember that your lower number is given to that side group or substituent which has the alphabetical order, which has the first alphabet coming in first. So here you have ethyl and here you have methyl. So because E comes before M, we are giving ethyl the lower number. I mean that side group the lower number. So it would be 2 ethyl, 4 methyl, pentane. Ma'am, in the case of tertiary carbocation, why are we counting the hydrogens of substituted groups as alpha and not as beta? See, in case of carbocations, what we are generally talk about, whenever we count our alpha hydrogens, that deals with the main thing that we are talking about. Say if I am talking about an alcohol, so in that case of alcohol, if this is my tertiary alcohol, I would say that this is my alpha carbon and that is my beta. But then when the reaction happens, say if I'm like substituting it with a Cl, then in that case I know that in the first place itself, you will have the formation of the carbocation, which is now CH3, CH3, CH3 with a plus charge here, plus OH minus. So now this OH minus has already been lost. So in this case, my now primary focus or the main function which is like operative is your carbocation. It is this plus charge. Now it has lost the identity of the alcohol. It is no longer an alcohol. It is rather an ion. So in that ion, I will call this as the main focused atom which contains the ion or the charge, and the other carbon atoms which are immediately attached to that carbon as the alpha carbon atoms now. So here we count this as the alpha only and not as beta. But if your functional group is there, then you have to look at the alpha beta accordingly. So do not keep any confusion for that. Okay, where were we? Nomenclature. Alright, quickly I will put down the order of preference for you, and please try and remember it. See, the more the number of times you write it, greater are your chances of memorizing it, or the more nomenclature you practice, for which I know that you are too busy. So what you can do is at least do the order of preference, just glance through it once whenever you open up your notebook. So it is like something which should be kept very handy. Your carboxylic acid and sulfonic acid, sometimes in some of the books you find the interchanged role also. But in that case, you can just take your call according to the preference that can be given. Normally not put together ever. Sulfonic acid and carboxylic acid are given the highest preference, followed by your ester. See, acids are given the topmost priority, and remember that after that they are all the acid derivatives. You do not have to mug them up like anything, because by and large whatever two functional groups are given, they have such kind of difference that you can make out that this has a higher priority. So remember that the acids are followed by the acid derivatives. So you have COOR, then you have the acid halide, then you have acidamide, CONH2. Acidamide is your CONH2. Then you have cyanide, isocyanate, then you have aldehydes and ketones, out of which aldehyde is given a preference over ketones. And then you have, I'm just putting the order from here after to this page. So ketones have a higher preference than your alcohols, followed by your thiols, then your amines, ethers, and then cyclic ethers, or you have your double bond which has a preference over your triple bond, followed by your NO2, and you have X, and you have your alkyl groups. And for alkyl groups also I have told you how the preference is to be given. If it is for the same halogens which are attached, same halide ions which are attached, chloro, fluoro, then also you can follow the alphabetical order. No other concept of inorganic which is to be applied here. This has been taken care of. So here you have acids followed by the acid derivatives. Why do we call them the acid derivatives? It's like a simple thing, because they are derived from the acid itself. What you have is, like, say if you have RCOOH and you have another RCOOH. Okay, this is what? This is your ester. If you have RCOOH plus RCOOH, then in that case you add P2O5. P2O5 is what? It is a dehydrating agent. तो वो क्या करेगा? पानी निकाल लेगा. Dehydrating, hydrating means water. So it will take out water from here, and what will you get is R, C, double bond O, O, C. So this will be your ester. And I hope you remember the naming of the ester. It will be, it is generally named as OH. So whichever is the smallest function, then you can name it accordingly. Oh, this is like not an ester. I'm sorry. Ester is your COOR. I did not draw the ester. Rather, I showed it to you something else. But generally, this is also an acid derivative which occupies a place here. So you can just put it as ester are also derived in this fashion. You have RCOOH. Say you replace them with an RCl, any kind of an something that can actually abstract your hydrogen from here. Some kind of a base also will do if you add in NaCl, KCl or something, then in that, or you add an HCl also, it will take up the water. You can have R, then in that case COO, and you have your R dash here. Your HCl just gets eliminated. So your HCl will just get eliminated and you will get your RCOO R dash. What you have to remember is that it is also a kind of an acid derivative. This is also an acid derivative, so it also will be given a higher priority. And this will be your, now this will be your OH, not this one. This is your anhydride. Why an anhydride? Because the hydride part of it has been taken away. So this is your acid anhydride. And generally they can be mixed up only with any other functional group when it is placed along with your R group. So that can be named accordingly. So here what you have is RCOOH. When it reacts with some kind of a compound wherein you get an alkyl group substituted in place of H. So this is your RCOO R dash. And then similarly you can have your RCONH2 also, like say for example RCOOH, and you are adding some kind of an say NH, alright, NH3 is like not suitable, let me just add NH4OH, alright, that's aqueous ammonia, so NH4OH. So in that case what you can have is NH2 can come here, RCO NH2, your OH goes off from here, RCONH2, and plus you can have water. So this is your acidamide. So that way you can actually try and formulate your reactions from the basic understanding that you know that OH has to be eliminated and it has to be substituted with some other compound or some other group, sorry. So then in that case it becomes acidamide. Clear with that? So all these acid derivatives are given a preference after acids, followed by your aldehydes and ketones, and then you have your cyanides, isocyanide, and then you have your aldehyde ketones, and then the basic ones, alcohols, thiols, and amines, ethers. And please remember that all these have a prefix as well as suffix. I am not taking it up because it's given in almost all the tables. Like for example, when this is as a site substituent, say for example, I can take up any example saying that this is OH, alright, and then you have CH2, COOH. Where will you start the numbering from? From the parent functional group which has the highest priority. In this case, you know carboxylic acid anytime has a higher priority than your OH. So you start numbering from here. This will be a 1, 2, 3 and 4. Now on 3 you have a substituent. So a side group which is attached, functional group which is attached, and for this the prefix generally is like hydroxy. So you will have 3-hydroxy butanoic acid. Alright? This will be like 3-hydroxy butanoic acid. You can put a 1 or not, that's like understood. So if you put 1, that is also not wrong. If you do not put it, then also it's fine. Alright, so remember that this order of preference plays the major role in your nomenclature. After the nomenclature, I think you can have some nomenclature of different compounds as well. Now when we talk about say the nomenclature of something which is having all the 3 groups attached to it, then in that case, like for cyanide sometimes it's like a doubt whether we should be counting up the carbon or not, because for aldehydes you start from the carbon of the aldehyde and then you name it propanol, butanol, al with an Al. Alright, that's the suffix, and remember the prefix also for each one of them. Then in this case of cyanide you have CH2, CH, Cn, and then again you have a CH2, Cn here. Now it is sometimes a problem because if you start numbering from the carbon atom, it will be named as a nitrile. So rather than that, it is also preferred when you have more than one functional groups of the same one, you can also go about doing it as like 1, 2 and 3, and then name as propane 1, 2, 3 cyanide. There's nothing wrong in it. You can also name it as propane 1, 2, 3 cyanide. So that's not wrong at all. Alright, and you can have similarly the names of certain different things. See, the basic ones are the ones which are dependent upon your order of preference and something of which you are doing regularly now in your 12th grade. Like you start with alcohols and you do the naming of the alcohols. Then you start with your next ketone, aldehydes and ketones, and you do the naming with them. When is it different is like when you take up some different kind of compounds like alicyclic compounds, which are generally asked in the jam as well. What is this? Simply cyclohexane. इसमें तो कुछ doubt ही नहीं है. So this will be your cyclohexane. Now what is this? Cyclohexene, because you will start the numbering from your functional group itself. And then if I put an OH here, then in that case you will start the numbering from here now. So it will be now 3, 4, 5 and 6. This is your hexenol. Alright. So you can actually put it as hex 2-ene 1-ol and 1-ol, or it is understood that your ol will be attached to the first carbon. So if you put it as 2-hexenol also, hexenol, remember that E should be there. This is representing your ene. So it is understood that ol will definitely be at 1. So your ene is at the second, starting at the second carbon. So this is like one and the same. Both are correct. Then let me just give you a little more complicated one. Say this is this, and this here you have CH3, and you have a CH3 here again. So what about this case? Here your numbering will start from the side group only, wherever you have a side functional group. So you will have 1, 2, 3, 4, 5, 6, that's like visible. Now for the side group, if it is like an elongated chain with some extra additional groups attached to it, then in that case you can look for the longest chain from wherever. If the longest chain goes to the right, go to the right. If the longest chain go to the left, go to the left. So we start naming our side group according to a new numbering system which starts from the first point of attachment. So we start from here. This will be 1, this will be 2 now. That's it. You go to the left or right, this was like similar. So here you have 1, and you have, now you will have to name this. It will be, this is now your side main group. So this is your ethyl, and that ethyl also has a methyl attached to it at number 1 position. Got it? This entire side group is at 1 position. So at the first position, I start naming my side group now. That will be my 1, first letter capital, right? It will be 1 methyl, and then you have 1 methyl, ethyl, right? Because this is your ethyl. 1 methyl is a side group to your ethane wala chain. So that is your ethyl, and then you have cyclohexane. Got it? Remember that you have to focus your, this is your side group, side functional group only. So it will be named as a prefix only. But while naming that also, you have to check whether that side group also has a side group or not. And in this case, one of them will definitely be a side group because you have to proceed either to the left or to the right. So whatever is like leftover will be your side functional group. And then sometimes even as complicated as a side group to a side group can also come in between. But that I don't think will go to that extent. Okay, then let's name this one. If you have a cyclic chain along with an open kind of a functional group, so then in that case, you will be giving the preference to the longest chain. Here, how many are there? Now, I mean, you will not name it as, see, what is this? 1, 2, 3, 4. So it can be butyl cyclopropane, which is wrong. It will not be butyl cyclopropane because you can think of butyl as a side group and you have a cyclopropane here. But that won't be the case. No. Why? Because butane is a longer chain. It has greater number of carbon atoms than your acyclic, then your cyclic chain group. So in this case, your cyclopropane will be your side group. So then in that case, it will be the side chain will be your cyclopropyl butane. cyclopropyl butane. So take care of such tiny things. Done with it? Then I'll give you one problem to solve. In your order of preferences, I think the cyclic compounds also are like almost at the same level as the alkyl groups. So you just check out which has a bigger number and then name it accordingly. The one which has a bigger number will be your parent name. Now what if it has the same number on either side? Say if you have this, alright, this is your cyclopropane chain, and then you have CH2, CH double bond, CH2. Name this. And then name another one. Double bond O, CH3, and then you have CH2, CH3. One. You decide. Do it quickly. For the first one, remember that you have a double bond also. So what will you have? Where will you start the numbering from? From the extreme right. Because your double bond and triple bond anytime have a greater preference than your alkyl chain. So 1, 2 and 3. And at 3 you have your cyclopropyl chain. So what will you do? This will be 3 hyphen cyclopropyl, and then you have prop 1-ene or 1-propene. Number in this case is important because it could have been a 2-propene also. Alright? Okay, if it was this, name this as well. CH, double bond CH, okay, CH3. Equivalency satisfied. Alright. Number this. So in this case, where will you start the numbering from? 1, 2, and 3. Your side group remains as cyclopropyl. So now it will be 1 cyclopropyl, 1 propene. Okay, now for the next one. The next one has a double bond O also, a keto group attached. So you have 1, 2, 3, 4, 5 and 6. The numbering should be in such a fashion that all your functional groups should get the lowest number. Your side chain should, so that is why we are moving from the right. Your main functional group is the ketone group, so the suffix will be -one in this case, alright, and then you have 2 side groups also here in this case, 2 side chains. So this will be named as 3-ethyl, 2-methyl, alright. Cyclo is missing. Sometimes you actually tend to forget about the cyclo when you have to subjectively write it. So cyclo, hex, very good, 2-ene, 1-one. And remember that whenever this ene is put here, do not put this as ene. That E is like missing, the final one. Then this is for the cyclic compound done. We can also have spiro compounds which can be named according to the starting with the name spiro. It is generally like a prefix of spiro is used for these spiro compounds. When we talk about these spiro compounds, what are these spiro compounds? They are the ones in which carbon is attached in between 2 cyclic rings. And when we talk about the carbon attached to 2 cyclic rings, how does it look like? Let's take up an example. In this case, say for example, if we have this and this, alright. Here, your carbon is attached in between these 2 rings. So this is like a carbon coming in between, and this is a spiro compounds. So remember that always a prefix of spiro will be used for such compounds. So sometimes it may be the case that you have one of the options only with spiro, then you don't have to work it out also. And if the other options are not carrying that spiro, you can just straight away take that answer. So if you have this, in this case you start numbering from the lower chain first, this whichever has the lower number of carbon atoms will be named first, and here in this case count the number of carbon atoms in each. Say it will be 1, 2, it goes in continuation. Just look up here, it will be 1, 2, 3, 4, 5, 6, 7 and 8. It will go in continuation only. So the name will be octane only, but how will you name it as spiro, so that you get to know that there is a spiro chain which has 3 carbons on one side and it has 1, 2, 3, 4 carbons on the other side, 3, 4, and you will name it as octane. Clear? Remember that spiro compounds are those in which your carbon is actually some kind of a nanolie between the two other rings that are there. And we are not putting any cyclo-viclo because it is understood that if I am writing it as a spiro, there is a carbon which is attached a common point between the two rings. And it is not like this one. If you have, this is a bicyclopropane ring. So you have a propane, cyclopropane here and a cyclo. So this is not a spiro compound. A spiro compound would be only if you have the point which is in common and you have the carbon atom here. And remember that the numbering will go in continuation starting from each side. So it will be 1, 2, 3, 4 and 5. So the main name will be pentane in this case, right? Yes, pentane, and you will just write spiro in brackets 2, 2 so that it is understood. Okay, I'll give you one more spiro, just one more. Say a little bit of an extension. All right. All right, name this. Remember that the lower most, you start numbering from the lower ones first, because the lower numbering will first come in the brackets. And it is a spiro, why? Because your carbon is a common point between the two rings. So it will be spiro. No, in this case you have an oxygen also. Otherwise you can just name it the normal way that you've learned. Remove this oxygen and then name it. I will put the oxygen also now, later or sooner. So you have 1, you start numbering from the lower one, 1, 2, 3 and 4, now 5, now 6, 7, 8, 9 and 10. The normal way that you've learned, it will be spiro, in brackets you will be writing 4, 1, 2, 3, 4, 5, 4, 5 and then it will be your decane. Okay, now if you have an oxygen here, this was the only difference that I'd put. I'd put an oxygen here, it will become 6 oxaspiro. Alright, because of that oxygen, it becomes, the prefix that will be used will be oxa. It will be 6 oxaspiro and then you number your chain accordingly 4, 5 and you have 4, 5 decane. The rest of it just remains the same. So just in case if you have an additional group also, you do not have to worry, just go through the options which are there and you will be able to make out. Normally not asked for the CBSE examinations ever. So you should have an upper edge for the questions in JAM. Then we can even name the bicyclo compounds. If we have the naming of bicyclo compounds, bicyclo is like now different. In bicyclo, it is like you have a kind of a bridge in between. Say bicyclo compounds will be, let me just give an example to you. Say 1, 2, 3, 4, 5, 6, 7 and then you have 8. If you have a bicyclo compound, bicyclo compounds are the ones which do not have any carbon common point, but rather they have some kind of a bridge getting formed. Now here in this case, this was the only carbon that was a common link. Here you have two common links. You have 1, 2, 3, 4, 5 and then you have a common link between one carbon atom and 5 carbon atom, and there's another carbon atom in between. So some kind of a bridged atom is there. So whenever you have a bridged atom, and you can see two cycles running. So one cycle includes this 1, 8 and 5, another cycle also includes this 1, 8 and 5. How to start the numbering? The numbering can start up from one of the common links that goes in continuation as 1, 2, 3, 4 and 5. Now you will take care that the biggest one is like gone ahead first. So here you had 5 carbon atoms, then you left with only 2 more, 6 and 7, and your bridged carbon atom will be given the last number. You will come on to the bridged carbon atoms in the end, so it will be 8. And here, now it will be like something similar. You will name it as bicyclo because you have a bicyclo chain here, and the prefix is generally based on bicycle name. So it is bicyclo, and you have in brackets 3 on one side, 1, 2, 3, and then you have 2 on the other side, and then last would be the number of bridged carbon atoms. How many bridged carbon atoms? 1. We've taken 1, 2, 3 carbon atoms on one side. Bridging is of course done between 2 carbon atoms already. So you will be counting the number of carbon atoms on the left hand side, then it will be 2. So 3, 2, and then you have to talk about the bridged. So 3, 2, 1, and then you name it to give it a totality picture that the total number of carbon atoms all in all are 8. So that will be octane. So when you go back, you will first segregate this one. Say if you have to go back to the structure from here, how will you go about doing it? पहले तो bridged carbon atom को अलग कर लो, ठीक है? Bridge को अलग कर लिया तो octane में से कितने बचे? 7 carbon atoms. So that means it is some kind of a ring which has 7. So 1, 2, 3, 4, 5, 6, and you have 7 here. Alright, so 7 atoms. Then 7 में you have 2 on one side and 3 on the other side. So 2 on one side and leave 3 on the other side, join the other 2. कितने बीच में डालने हैं? That will be 1. So it will be like this. So you can go back to the structure also from the name. Okay, I'll give you just one more example for this. Watch out carefully. I'm just drawing this. Alright. Then just completing the structure, and then you have 1 carbon here. This has been asked. Alright, now number it accordingly. This is again a bicyclo compound because it is like a bridge between 2 carbon atoms. So bicyclo, starting the numbering from any of the sides which is supporting your bridge. So you started from here, 1, 2, 3, 4. Where should I go? Up or here? One and same thing. This is also kind of a bridge here. So 5, and then the last number to be given to 6. Sorry? Where the lines are intersecting, can't we assume a carbon there? Here, no. This is only a picturization of the system on the board. Otherwise, they're not touching each other. One plane is like this and the other bridge is like this. So, वैसे actual में तो touch नहीं कर रहे, a board में touch कर रहे. तो, otherwise, it is like you have one triangle here and you have another 4 points here, and then this bridge is like this. So, they're not touching each other. So, this is not a carbon point. Yes, here it is a carbon point. This is also a kata and this is also a kata. So how will you name it? This will be a bicyclo. Now in brackets you tell me. How many carbons on one side? 2. How many on the other side? 1. How many bridged? 1. And then your name? Did you name it correctly? Could you? So it will be bicyclo 211 hexane. Just go through the spiro and the bicyclo ones carefully, and then we shall go on to some common names which are generally in use and need to be remembered. Remember that spiro compounds are the ones in which your carbon atom is like a common link between the 2 rings, and it is like a point of attachment of the 2 rings. So we start numbering from the carbon atom which is adjacent to that particular point, and the lowest ring first. Remember that the lowest ring first in this case. Whereas in case of bicyclo, we go ahead with the bigger ring numbering first. So we name the bigger ring first and then go ahead with the smaller one, and then we talk about the bridged carbon atom. Here in this case, we just do not talk about any bridge because in spiro means only one is the common point. So once and for all, final. Bicyclo, as the name suggests, bicyclo, it's being attached from two sides. Alright, and then there is a bridge between those 2 points. And that bridge will be numbered as the last one. Then we move on to the naming of some of the aromatic compounds then. There is something which is known as a common name and something which is like your IUPAC name. So there should be no confusion for that. And in your ABCD questions to CBSE, there are so many a times that the common names are given and you're supposed to know the structure for that. So in this, if we go ahead, first of all, you start naming. What is this? All right. Then what about this? Benzene. All right, I keep changing this. I won't have to draw. Let me just draw a bigger structure. All right, this is your chlorobenzene. जो benzene ही बार-बार draw करना है, तो let me just draw a bigger structure. So this is your chlorobenzene. What about this one? Toluene. All right, and then if I just change it to OH, keep naming them. Phenol. Very good. Now if I change it to NH2, aniline. All right, when I change it to COOH, benzoic acid. Not even a single student should be naming that wrongly. And then you have your benzaldehyde. You're doing the qualitative analysis in organic practicals as well. So this is like something which smells like almonds. So the moment you get this, you will get the smell of the roasted almonds. So that is for sure your benzaldehyde or some derivative of benzaldehyde. Okay, and then you have, what is this? If you're saying benzo, it doesn't make sense. It is benzo whenever you have a carbon atom attached to the benzene ring. So it is benzo nitrile then. That's what I stated. Whenever you include the carbon atom in the numbering, then you name it as nitrile. Otherwise as cyanide. So you can either name it as cyanobenzene or benzocyanide, not benzocyanide, benzonitrile. If you're putting that O in the end, then in that case it will be benzonitrile. So this will be, I'm just putting the name because there was a little confusion for this. This is your benzonitrile. All right, next, okay. Then if you have CH2, CH2 or NO2, if I put an NO2 here, nitrobenzene. Okay, if I put Cl here, common name first, orthodichlorobenzene. This is ortho, this is meta, this is para. Alright, this is orthodichlorobenzene. If I put it here, then this will be meta, and the naming will be like, in this case you said 1,2-dichlorobenzene. In this case it will become 1,3-dichlorobenzene. In this case becomes 1,4-dichlorobenzene, and the common name will be para-dichlorobenzene. Okay, that is understood. Now let me just change it a little bit for your naming. Okay, take this CH2, 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 Br. How will you start numbering in this case? Remember that because you have a Br here, alright? Br, and you have here the chlorobenzene. In this case, your side chain will be given the preference, which is your propane. Okay? So if propane is given preference, where do you start numbering from? You start numbering from here 1, 2, and 3, because your main functional group, you counting it as bromine. Alright, did I give you in the order of preference how the halides are to be taken? No, I'll just give it to you. So in this case, you have bromo, and then you have at the 3. So now at the third position, what will you have? You will have 3, 4. Why? Because at 3 position, what do you have? 1, 2, 3, and 4. So you can have 4 chlorophenyl, because whenever your benzene ring becomes a side chain, then it is called a phenyl. 4 chlorophenyl, and then you will have simply either Bromo because it is named first, so you can actually put it as bromo here also. You can have bromo here as well. Bromo, then what happens in the bromo chain? You have the bromopropane chain, and in bromopropane chain, your third number of the propane chain has 4 chlorophenyl group. So it will be bromo 3 4 chlorophenyl in brackets propane. All right. And then whenever you start off with your mechanisms, in your mechanisms you talk about the fissions also. All right. Fissions can be of different types. So we'll just quickly look at them. Can you just take it off? I have taken up some of the different things that are generally asked. I hope you do not want me to take up the nomenclature in details because there are other aspects which are to be discussed. Remember that if you go through the prefix and the suffix carefully and take up some examples round about 40 to 50 at one go, you will become absolutely clear with nomenclature. Just go through the book. I mean, even your NCRT has different types of examples in your 11th grade books. I've gone through it. So remember that you go through the order of preferences and try naming it on your own, and you will get the hang of it within say 10 to 15 minutes only. And now I was talking about fissions, yes. So now if I talk about a homolytic fission, see, a homolytic fission is the one in which the bond is equally shifted in both the direction. Homo means similar. Lytic means tootna. Lysis means breaking. So whatever you have is, like in homolytic fission, what generally happens, this is like, you know, an electron pair. So if it gets half shifted here and half shifted here, then what kind of a fission is happening? You get, and this is generally in the presence of sunlight or a photon. So you have A plus B, and these are termed as your free radicals. These are generally termed as your free radicals. Remember that whenever you talk about the homolytic fission, they are generally occurring in the presence of sunlight only. And whenever you talk about some kind of a polymerization reaction, which you will be doing in 12th standard, in polymerization reaction, there are 3 main steps. One is the chain initiation, then you have the chain propagation, and then you have the chain termination. There, by and large, the mechanism which is operative is because of the free radicals which are generated. So in your initiation step, what is done is your free radical is generated. And remember, in your termination, and then that free radical is like carried on forward with the other molecules to just keep on attaching. And your termination always is a combination of 2 radicals. So when you break them up and generate free radicals, they set up a chain reaction always. And whenever you have the combination of 2 free radicals, they will always terminate a particular reaction. So that is something which needs to be remembered. Like for example, if you have Cl2 in the presence of sunlight, then remember that it will always be giving you 2 Cl radicals. They are highly reactive, neutral and electron deficient species. They are counted as electron deficient species. Otherwise, generally when we talk about the electron deficient species, you can either have electron deficient species or you can have an electron rich species. Please remember it very clearly that electron rich species are your nucleophiles. जो भी इलेक्ट्रॉन में रिच होगा वो होगा न्यूक्लियोफाइल, and whatever is deficient in electron will be your electrophiles. All right, will be your electrophile. Now if in case I am saying that this is electron deficient, why? Because it is not having a full pair of electrons, it is having only a single electron. So that is why I am calling free radicals as a separate entity. Remember that free radicals are generated by the homolytic fission. If I talk about the heterolytic fission, if in heterolytic fission I have a molecule AB where B is more electronegative than A, you know what is the meaning of electronegative? The tendency to pull electrons towards itself. So if B is more electronegative, it will pull this electron pair towards itself. ठीक है, अब ये इसकी तरफ अगर आएगा तो जो देगा that becomes positive and the one which takes up becomes negative. So then in that case the homolytic fission will generate A plus and B minus. Now the total pair of the bonding pair of electrons which initially was there has shifted to my B. Okay, so now B, when the one which has a negative charge has more electrons, so this will be your nucleophile. तभी जितने भी हमारे negatively charged species होते हैं, all of them all are your nucleophiles only, and the ones which have a positive charge are your electrophile. So this is an electron deficient species because कई बारी it's like a misnomer. बच्चे confuse हो जाते हैं. When we talk about electrophiles, they feel electron, तो ये electron rich होगा. Please remember it at least by telling yourself 5 times right now that electrophile means electron deficient species. और deficient मतलब positively charged ions, because positive का मतलब है they've already given, and the one which has given means that it is deficient now. So your A plus will be counted in your electrophiles. So if I am writing OH positive, what is it? It is an electrophile. If I am writing NO2 minus, it is a nucleophile. If I am writing Cl minus, it is a nucleophile. If I am writing Cl positive, it is an electrophile. So accordingly you can just now label your electrophiles and nucleophiles. But remember what is an electrophile and what is a nucleophile. Okay? यहीं से एक चीज समझाती हूँ. Let me just see as to what is next. Yes, I was talking about this only. I have talked about fission now in your organic chemistry, which is important to understand some mechanisms also. Free radicals are generated by and large in the presence of sunlight only, and they are generated by homolytic fission. Heterolytic fission generates two types of ions, cations and an anion. The one which is like the cation is your electrophile, and the one which is an anion is your nucleophile. Electrophile means it is an electron deficient species. Nucleophiles means it is an electron rich species. Any confusion to anyone? Am I going fast? So now in the next case, say that is why when we talk about the reactions of your alkyl halides or generally alkanes, say if I have CH3 Cl and my incoming nucleophile is like OH minus. What is this? OH minus. What is it? A nucleophile. Why? Because minus. I had to ask that question. I said that. OH minus, and that can be generated from any of the aqueous bases, strong base. NaOH ले लो, KOH ले लो. तो there is no hard fast rule कि अगर book में NaOH लिखा है तो NaOH ही चलेगा और कुछ नहीं चलेगा. You can just apply your mind and apply similar kind of logic also there. And why do we generally use NaOH and not KOH? Yes. So in this case, what will happen? Your Cl minus will be replaced with OH minus. So because एक Cl minus charge निकलेगा तभी तो OH minus charge लगेगा. Are you getting the point of that? So in this case, what you have is you have CH3OH, all right, and your Cl minus will just go out. So in this case, I want to draw your attention towards this fact that one nucleophile, Cl minus निकल रहा है, OH minus लग रहा है. One nucleophile is getting substituted with another nucleophile. So that is why this is called as a substitution nucleophilic reaction. Alright, this is known as the SN reaction. Alright, now you have two types of substitution nucleophilic reactions. One is your SN1 and the other is your SN2 reaction. अब SN का मतलब तो समझ में आ गया कि it is the substitution of one nucleophile with another nucleophile. So we call it substitution nucleophilic reaction. Now say for example, in this generally we are making use of some kind of a heterolytic fission which is happening. Nobody asks you, but you should just know. So इसके अंदर we are generating some kind of a nucleophile from our reagent which is getting added up. So if say for example, if you have a tertiary one, a tertiary alkyl halide, this is like a compound which can be formed from your alkanes, which is 11th standard, which we are precisely revising right now. So if you have a tertiary alkyl halide, this is your tertiary alkyl halide, and I am attaching an OH minus to it. What generally happens is this OH minus will attack from some place where it gets space. अब tertiary में क्या है? You have three bulky groups attached. Bulky means बड़े-बड़े. So you have three bulky groups attached. In the presence of these three bulky groups, होता क्या है? OH minus के पास कोई जगह ही नहीं है. It will just ask, not ask, what generally happens is it will just ask this particular molecule to just remove the Cl minus first so that a place is created for it. So in this case your OH minus cannot attack in one go directly. And what happens because of this is like it undergoes one step first, and which is like CH3. It will first generate your carbocation which is highly stable, right? It will first generate your carbocation which is highly stable. एक बार वो carbocation generate हो गया, उसके बाद next step में there is no need to write, just understand here. Look up onto the board. Now once this carbocation is generated, now there is ample space for your OH minus to come and attack. Alright, this OH minus will just come and attack here. So there will be a retention in the configuration also, क्योंकि जहाँ से Cl minus निकला वहीं पे हमारा OH minus लग गया. Now there are different aspects to this organic reaction. First of all, this is our substitution of nucleophile. So this is Sn, alright. But this is our rate determining step, in which in our rate determining step only one molecule is involved. So this is known as your SN1 mechanism, alright, which is happening in two steps. So confused nahi hona. In this case, your OH minus, the incoming nucleophile cannot attack in the first step. Had it attacked, तो हमारे दो reactants हो जाते. दो reactants कौन से होते? एक तो हमारा alkyl halide और दूसरा हमारा OH minus का reagent, which may have been your KOH, NaOH, whatever. Alright. So in this case, what happens is your Cl minus leaves first. एक बार Cl minus चला गया तो हमारा carbocation generate हो गया. Then it's like the normal reaction that is happening. So because this is substitution nucleophilic and you have only unimolecular. Alright. This means it is unimolecular reaction. Alright. That is why this is SN1. And then remember, what is a special feature of your SN1 reaction? It is it results in the retention in the configuration. Because whatever was the initial, we'll talk about these configurations and other things just now, but because now I have started with SN, so let me just complete it. So you have your SN1 here. Clear with that? Now let's move on to the next one. Now if you have had a primary one, primary is like C, alright, OH, and you have 2H, alright, tetrahedral shape, so just assume it accordingly. So if you have OH and say your OH was a little like this, alright, no, alkyl halide is what we are talking about. So if you had your Cl here and now you have to attack it with an OH minus, your OH minus can come from any of the positions because only one bulky group may be attached. If it is a primary alkyl halide, you know that the chain of the alkyl groups goes in one direction and the other two positions in tetrahedral position are occupied by your hydrogens. So they are not as bulky as your alkyl group. So then in that case your OH minus can attack from the opposite side from, or I can put it like this. What is this? You have your CH3 here, you have your C, H and H, alright, and you have your Cl. Alright. Now in this case there is enough space because these hydrogens are not as bulky as your alkyl group. So my OH minus can come in and attack from any position which is opposite to my leaving nucleophile. This nucleophile will leave and this nucleophile will come inside. So then in that case I will have CHH, temporarily say my OH is coming here. This is like a simple transition state which is involved, and you have Cl, which is also at the leaving state, so dot dot dot, and then you have CH3. Remember that your transition states are temporary states because they are highly unstable. So immediately you will get your CH2 and you will have your OH on the other side. So there is an inversion in the configuration this time. पहले इस तरफ Cl था, अब OH इस तरफ है. So there is an inversion in the configuration, and then this kind of a reaction which is like again substitution nucleophilic. This is your bimolecular because both the molecules are reacting right in the first step only, and a single step reaction. Okay, so this is your SN2. Then electrophiles are done. Electrophiles are your electron deficient species. Nucleophiles are your electron rich species. There is some species which are known as amphiphiles also. Please make a note of those also. Some species which are known as amphiphiles. And what are amphiphiles? Amphiphiles are basically the ones which have both an electrophile and a nucleophile in them, which is very simple to designate, like in case of ketones. This is aldehyde and ketones. You have HCHO, which is formaldehyde. So in HCHO you have say a delta positive charge and a delta negative charge here. So this positive will act as an electrophile, and this negative will act as a nucleophile. So you have such kind of compounds are known as your amphiphiles. All right. Then we've talked about the free radicals also, and remember that the free radical stability is also according to the number of groups attached to it. And just note down for the order of stability for the free radicals also. Did you all understand SN1 and SN2? Now remember कि SN2 will be now always preferred by primary, and SN1 will always be preferred by the tertiary. Alright, tertiary क्योंकि बड़ा है तो वो पहले single handedly it will just let Cl go off and then take up the OH minus in the next step. So because it is single handedly doing it, so SN1 for tertiary and SN2 for primary. And secondary, actually depending upon the kind of groups which are attached, it can either undergo your SN1 or can undergo your SN2. But the order can be mentioned now. Say if you are given 2-3 compounds, to tell up what will be the order of reactivity for SN1. Say if you're given a 3 degree alkyl halide, you're given a 2 degree alkyl halide, and you're given a 1 degree alkyl halide. So you have to talk about the order towards your SN2. So in SN2 you know is the maximum for your 1 degree, because 1 degree में दोनों एक साथ आ जाएंगे, enough space, so it will be this. If it is for SN1, then in that case for SN1 it will be this. Alright. And by and large, why is SN2 favored by 1? Because of less steric hindrance there. Alright. And why is SN2 not favored by tertiary? Because there is a lot of steric hindrance because of bulky methyl groups which are present. Now I'm just putting the order of stability for your free radicals. You have C6H5 whole thrice. C is like a free radical. Then you can have, this is like when you have 3 benzene rings attached, because this free radical then will have 3 resonating benzene structures alongside. So you have C6H5 twice, and then you have CH free radical. Then you have C6H5, CH2, which is again with a single one and free radical. Then you have CH2 double bond CH, CH2, which is again a free radical. And you can actually think about resonance also here, because you know that the electron will have the capability of resonating with the other double bonds which are present alongside. Then followed by 3 degree free radical. Now you know that free radical will also be somewhere linked to your hyperconjugating structures also, because एक बार H free radical निकल के it can attach and get a free radical there at that point. So 3 degree, and then you have a 2 degree, and then you have 1 degree, and then you have the allylic CH2CH radical. Remember that the allyl radical, free radical, is the least stable. Then for the carbocations also, just note it down. For the carbocations will be your electron deficient species, like you will have C6H5 thrice, and then you have the same order C6H5 twice of C plus, CH plus, and then you have CH3 thrice, C plus, then you have C6H5. In this case, you have the hyperconjugating effect operative being more predominant, and the inductive effect being more predominant over your C6H5CH2, the benzyl carbocation. Whenever a CH2 is attached to your benzene ring, it is known as the benzyl group. So this is your benzyl, followed by your, this was your 3 degree, and this is your 2 degree, followed by your CH2 double bond CH, CH2 plus. It's just the same with just a little bit of difference. C6H5 carbocation plus will be on C, alright, and then you have CH2 bond CH. free radical. Okay, and I'll put it for the carbon anions also. This is for the carbocations, and for the carbon anions you have C6H5 thrice, C minus greater than C6H5 twice, CH minus which is greater than C6H5, CH2 minus which is greater than CH2, CH, CH2 minus, alright, and then which is followed by your methyl anion, 1 degree and 2 degree and now 3 degree in this order, and followed by your carbon ions. Okay, this is for your carbon ions. And then what are carbenes and nitrines? Remember that whenever our carbon, how are carbenes generated? पहले समझ लो carbenes होते क्या हैं? Because now less time is left, let's just quickly take up each and every aspect from the top. What is a carbene? Whichever has a lone pair of electrons residing on the carbon. और ऐसा कब होता है? When two substituents or two groups leave from the same carbon atom. Alright, whenever two groups leave from the same carbon atom, then in that case you have the generation of a carbene. Okay, with two bond pairs. Now here in this case, like for example, you can have the generation of carbenes from a ketone like CH2 double bond. This is a ketene. This is known as a ketene, and in the presence of H nu, this is generally something that is not given but is asked many a times in the examination. So a carbene is generated. Now here the two double bonds will be these, the double bond here, plus you have CO. Alright, these are like electron deficient and behave as Lewis acids generally. Alright, you can have a singlet carbene or you can have a triplet carbene. Carbene can be of two types. You can have a singlet carbene, ट्रिपलेट. पहले ना इस सिंगलेट और ट्रिपलेट का मतलब समझ लो. दिस गिव्स यू द स्पिन मल्टीप्लिसिटी. योर स्पिन मल्टीप्लिसिटी इज एक्चुअली गिवन बाय अ फॉर्मूला. स्पिन मल्टीप्लिसिटी इज गिवन बाय अ फॉर्मूला ऑफ 2s plus 1. ठीक है, spin multiplicity, please remember this, is given by a formula 2s plus 1. And if it has टू इलेक्ट्रॉन्स, इसका मतलब इस कार्बन के पास दो इलेक्ट्रॉन्स हैं कार्बीन के केस में. सो इफ इट हैज टू इलेक्ट्रॉन्स, देन इन दैट केस रिमेंबर दैट अगर सिंगलेट है तो इसका मतलब उसका स्पिन इज लाइक स्पिन मल्टीप्लिसिटी इज इक्वल टू 1. और वो 1 कब होगी? जब ये दोनों इलेक्ट्रॉन्स जो हैं दे विल बी विद द ऑपोजिट स्पिन. बिकॉज ऑपोजिट स्पिन का मतलब है स्पिन कितना है? 0. एंड 2s plus 1 is my spin multiplicity. So that means 2 into 0 plus 1. So then in that case the spin multiplicity will be 1, which means it will be a singlet carbene. Okay, a singlet carbene is, it has a bent structure, and remember it is less stable than your triplet carbene. Singlet carbene is less stable than your triplet carbene. अच्छा, and then carbene के केस में जैसे you can have a triplet carbene when you have, see, singlet ground state is this. All right, when I excite this, ये क्या हो गया? सिंगलेट एक्साइटेड स्टेट. ये सिंगलेट ही है अभी भी क्योंकि स्पिन 0 है, अभी भी ये 0 है स्पिन, बट इन दिस केस आल्सो द स्पिन इज लाइक सिंगलेट. सो दिस इज सिंगलेट एक्साइटेड स्टेट. एंड व्हाट इज दिस? दिस इज योर ट्रिपलेट एक्साइटेड स्टेट व्हेन दे हैव द सेम स्पिन. और सेम स्पिन का मतलब हाफ प्लस हाफ. सो दैट मीन्स 2 into half plus half is your 1. Spin is 1 plus 1. So 2 1s are 2 plus 1, it will be your 3. So now this will be a triplet carbene. Whenever you have the spin of both the electrons as same and not opposite, then in that case the total spin will be equal to half plus half, which is 1, and the spin multiplicity will be equal to 2s plus 1, which will be 2 into 1 plus 1. So that is 3, and it will be a triplet carbene. Alright, now the order of stability of carbenes is very importantly asked in the examination. Please take a note of it. CH2 is greater than CF2, which is greater than CCl2, which is greater than CBr2. This is the order of stability of the singlet carbenes. And remember that a singlet carbene is always less stable than your triplet carbene. another thing that I want to, it's जैसे अगर if you have to generate CCl2, so what can you think of? Think of a molecule which has a Cl2 attached. So you can either think of CHCl3, ठीक है, इसमें से your H and 3 Cls are attached to the carbon only. If somehow you can slowly and steadily stepwise reduce first H and then Cl from it, it has to go stepwise only, then in that case you will get CCl2 from your chloroform as well. So you can think about any kind of a starting compound from which the elements should be taken out from the same carbon atom, and if you are able to develop or technique from which they are coming out from the same carbon atom stepwise, then you can get a carbene. So the order of stability of carbenes is important. Then remember that you have something which is known as a benzene also. Benzene is nothing but, you know, the normal benzene ring. This is your normal benzene ring. Whenever you have one of the two carbon atoms having a triple bond, then in that case it is known as the benzene. And in benzene what you have, these two carbon atoms have their sp2. You know that benzene ring normally has the sp2 hybridized carbon atoms. So these sp2 actually will be overlapping with one another to form the third bond. So it is the overlapping. This question has been put up in reasoning. So remember that in benzene, the third bond which is like formed, the triple bond which is like formed, is attributed to the overlapping of two sp2 orbitals. So it is also sp2 and this is also sp2, and you get a benzene. So I'll just put one method of preparation for benzene on the board. The method of preparation for benzene can be from your chlorobenzene itself. It is an intermediate which is generally formed. You have chlorobenzene and you add NaNH2 and ammonia. NaNH2 and ammonia to it, and then in that case what you generally get is a benzene intermediate before you get to aniline. So it involves a benzene intermediate followed by your aniline. Okay, and then we can just quickly talk about the inductive effect also. Inductive effect is just like the shifting of the paired electrons. Okay, this is also again a very important aspect that you generally do. We just did the stability of the carbocations also. We did the stability of the carbocations. We generally say that the reactivity of the tertiary halides is much higher than your secondary, which in turn is much higher than your primary. Tertiary is the most reactive if I talk in terms of reactivity. Now remember that whenever you have to talk about the reactivity, then in that case you talk about the stability of the ions which will get formed. इस केस में हम बोलेंगे कि that the third degree carbon ion is highly stable, but in order to form that carbocation also you should have some favoring factors. Cl, remember, is electronegative in nature. So what will it try to do? It will try to pull the electron density towards itself, right? Now these methyl groups or the alkyl groups also have a tendency to donate or share or push the electron density towards this neighboring atom. So if there is a need here, this carbon will be a little less on electron density because chlorine ने उससे maximum ले लिया. So there are three more groups which are donating their electron density and pushing it towards this carbon atom. Such kind of an effect is known as the inductive effect. Alright, and remember that inductive effect increases from the, say if you have Cl, this is your first carbon atom. If in case this is your second carbon atom, this is your third. It keeps on increasing till your third carbon atom. That means if you have, if I compare this primary with this, then the inductive effect will be more in case of this, followed by 1, 2 and 3. So you have CH2, I'm sorry, 1, 2 and 3. So in this case also the inductive effect will be operators till your third. So let me tell you, the inductive effect will be the maximum in case of this compound followed by this compound followed by this compound, because your inductive effect, that means ek had tak it will like it would be like appreciating the donation of the electrons towards the more electronegative atom. So it goes on to give chlorine more, which is like more electronegative. So remember that your inductive effect will be maximum in this, and wherever your inductive effect supports, जितना ज़्यादा वो electron density इधर देंगे, उतना ज़्यादा this chlorine will become more and more electronegative. So if it becomes more and more electronegative, so then in that case what happens, this polarity of the CCl bond will increase. और अगर polarity increase हो जाएगी, that is separation of charges, then in that case it is easier to cleave the bond. So here when we talk about now the tertiary, here I have only one point of donation that is coming from one side. So the inductive effect will be lesser in comparison to here where I have two methyl groups. So when I have two methyl groups, the plus I inductive effect shown by the secondary carbocation, the secondary group or the secondary carbon will be much more than the primary carbon because it has two carbons which are donating. So it will be more in this case. And when you talk about the tertiary one, the tertiary has three methyl groups in addition to now 2 and your 1 is as in case of secondary and primary. So that is why, because now they will show more inductive effect and this tertiary will have the most inductive effect operative in it, the polarity of the CCl bond will be the maximum. क्योंकि Cl उतना ही ज़्यादा खींचेगा जितना ज़्यादा कार्बन के ऊपर इलेक्ट्रॉन डेंसिटी आएगी. So in that case the CCl bond will be highly polar and so this will be highly reactive and quickly form the carbocation, which is again stabilized by hyperconjugating effect also. So this is followed by secondary, followed by primary. So this is again another important effect. The last effect that I want to talk about is the resonance effect, which is very, very, very important. And remember that there are some groups which show a plus I inductive effect, some which show a minus I inductive effect. And before I talk about, leave you for today's class, there is an important concept of resonance, which is also again very important. There are some groups which are willing to donate the electron density, and there are some groups which are willing to take up the electron density. And as you understand benzene has a resonance stabilized structure, तो उसके अंदर तो electron pair पूरा ही resonate हो रहा होता है. So I'll just quickly take up the last two examples. So in that case I have say Cl. अब remember that Cl shows minus I inductive effect क्योंकि it is electronegative in nature, but it will show plus R resonance effect. It will show plus R resonance effect because जो इसके पास lone pairs हैं, they will enter into the resonance with your benzene ring. So how will it enter? It will remember that electron pair towards the bond and your bond towards the atom. I normally teach it like that only. So what you have here is you have a double bond. अब Cl ने तो दे दिया, it becomes positive. So here you have a negative charge now and these two bonds remain intact. Now this electron pair will form a bond here and this bond will go to the atom. Now in this case, next case, we haven't touched your Cl positive at all, this bond at all. इसने एक bond अब बना लिया और ये bond अब इसके पास चला गया तो ये वाला carbon atom negative हो गया. Okay, अब similarly I'm just going ahead because of paucity of time. So what you have here is this will be forming a negative here and you have Cl positive here, and finally this negative bond, remember that charge always moves to form a bond and the bond will clearly move towards the atom. So here your Cl comes back and what you have is Cl. So here your plus R resonance effect is shown by chlorine. And remember that your negative charge is now coming at only ortho position and para position. So negative charge का मतलब ये electron rich है. So what can come and attack? Electrophile. So whatever comes into your aromatic reactions is always your electrophilic substitutions. And your electrophilic substitutions are always dominated by where your charge is in the resonance stabilized structure. And now the last one is where you have a minus R effect. See, the minus R effect can be obtained in case of aldehyde, carboxylic acids, etc. And this is the last structure that I am drawing for today to show your minus R resonance effect. You have a CHO. You know, oxygen is attached to carbon, which is highly electronegative. So in this case, your oxygen will try to pull the electron density towards itself. It will be so strong that this bond will now move towards another bond. When it goes to minus R, now it changes. Your bond is now moving towards this bond so that this bond shifts towards oxygen. And then in that case, now it is your positive charge which is actually getting delocalized within your benzene ring. So you have a positive because इस कार्बन ने दे दिया, इस कार्बन ने यहाँ से लिया, यहाँ से एक्सेप्ट कर लिया, ठीक है, और ये वाले ने ऑक्सीजन को दे दिया, तो ऑक्सीजन becomes negative and you have this as the structure. So this we did not touch these two double bonds at all, you have a positive charge. Now in this case it is simpler because a bond shifts towards a bond only. So this bond shifts towards this bond. So again it becomes what? This bond is, it comes here. अब इस कार्बन ने दे दिया, ठीक है? So this becomes positive. इस कार्बन ने यहाँ से दिया, यहाँ से took up the double bond, and this becomes CO negative, and you have your H. All right, and this double bond we did not touch at all. So now this double bond again shifts, and next what you have is, you have your CO minus, हमने इसको touch ही नहीं किया, we did not touch this bond. This double bond has now formed this bond. It has taken up, negative हो गया, neutral हो गया, this is taken and given, and you have a positive charge here. And now this double bond will come here, and your negative charge will come back again. And so in this case you have this coming here, and you have CHO again. So there is alternation of double bonds, and remember that even your benzene, so last thing is like even your benzene has alternation of double bonds, right? Your benzene, you can draw the resonance stabilized structure starting from any of the hydrogen atoms. You can just start up and shifting the bonds. So in this case this is clear, in this case your plus charge. So this, in this case wherever you have a minus R group, where you have the generation of now electrophilic sites, तो इसमें कौन सी substitution हो सकती है? Nucleophilic substitution. And अगर इसके अंदर हमें electrophilic substitution करानी है, तो electrophilic substitution will come where? It will come only at meta, because ortho or para are already electron deficient. So only electron rich site will be your meta. So meta पे ही attack होता है, and the reason for that is this entire resonance effect. Last but not least, your resonance effect is also primarily shown by benzene, जो सबसे पहले बात करनी चाहिए थी. You can even find out the bond order. Remember the bond order is nothing but bonds between any two carbon atoms. तो एक बार कितने हैं? अगर मैं इन दो carbon atoms को लूँ, तो इनके बीच में एक बार bond है 2, एक बार bond है 1. That divided by total number of structures. Total number of structures कितने हैं? 2. तो bond order कितना है? 3/2, which is 1.5. So you can find out the bond order also that ways. Alright, with this by and large we've covered more than 70-75%, but not completely. So that revises your last time's organic portion. Thank you.